The next one is a lot of fun. I was very pleased to read about this in this book. Now, the perfect cipher has been known for centuries. It's the one-time pad. If you just have a page of key, many letters that are random, and you deliver that to the person at the other end, and then you use each letter to encrypt one letter, like you use that as a measure of how much to shift for the Caesar cipher, for example, and you never reuse any part of the key, then there is just no pattern at all in the ciphertext. There's no mathematical way to reverse it. And in fact, it's even in principle unbreakable no matter what you do, because if you have a page of ciphertext encrypted this way, and you generate all possible keys, you will generate all possible combinations of letters, including every possible message containing that many letters. So many of them will be readable, valid messages, and you have no idea which one was being sent. So this is considered the perfect system. And the problem with it is key distribution. You have to somehow deliver enough key to the other person that it includes all the length of all the total messages you're going to send. And that turns out to be so difficult to do that it messes up the system. But really, all other hyper encryption systems like AES are just a way of creating a one-time pad mathematically and delivering it at the other end in a more efficient way. But it's not really perfectly a one-time pad, but that's what they're trying to do. They're trying to have a mathematical algorithm that will create this random pattern of bits at both ends efficiently. Anyway, so the one-time pad is in principle perfect, but the key distribution is a huge problem. And in World War II, the Russians used it, and they had the problem that keeps happening. They didn't have enough key, so they made these on a typewriter with carbon paper, and they decided to authorize using 4 sheets of carbon paper to make more than 2 copies of the key. So the same pad of key would be used for more than one message. And this encryption scheme is perfect, but if you use the same pad twice, it becomes terrible. It shatters like glass. And you can crack it without a computer at all if they use the same key twice. So here's a code that does this in Python. If you use this key string, which in principle it should just be random letters, but this is not as perfect. It's using a readable sentence as the key, and then I'm going to encrypt this message, 407. So that is this Python code. So this puts the key in a string and the plain text in a string, and then it just, for every letter in the plain text, it turns it into a number, the ASCII number, and adds and does an XOR with the key. All right, and so let me put this in a program, and you've got Python on your Linux box. If you want it, you can also put it on Windows. And so if I do nano, let's see, I already have this, OGP1. Yeah, that looks like it's already there. So if I just run that with Python 3, oops, I got to get out of here. All right, Control C, Control X, and okay, Python. All right, so here it is, letting you see how it works. 407 is the plain text. Unbreakable, awesome is the key. And you XOR them, you get these numbers, 13, 1, 7, 0, 45. And here they are, just hexadecimal numbers ran together. So that mess is the encrypted ciphertext. And if this is all you have, there is no way to reverse it. All right. You can decrypt it. It's the same operation. You just take the ciphertext and you do bytes from hex to recover it from these hex bytes. And then you can reverse it. So let me run that one. That's Python OTP2. All right, so here's those raw bytes, 19, 1, 23. Here's the key, unbreakable, secure, the same thing. And when you XOR it again, it just undoes itself, because XOR undoes itself. XORing again, because XORing flips all the bits that are 1 in the key, and XORing it again flips all the same bits again to restore them to their original value. So that's how you encrypt and decrypt in this system. And so here's a challenge where you just have to encrypt something with a key, And here's the crib drag. And the point of the crib drag is this. If you just guess that it contains, say, the word "the" somewhere, and you just load that anywhere really, in the key or in either one of the ciphertexts, then the rest of it becomes readable. The rest of this is unreadable garbage, but this is Nev and this is you. So now you can guess one of them a little more. Like this is Nev, maybe it's ER for never, or maybe this "the" is followed by a space, or maybe this "you" is followed by a space or an R. So you guess one of them and see if it makes the other two readable. And then you guess somewhere else, you just get a couple of characters one by one, and you can just walk right through the bloody thing. And if you want to, I found it helpful to write a little Python script that will make this interactive. So I think that's my OTP1. Python 3, crib1. There, this is it. So this is that thing, and I've just numbered it, so now I can guess one of these. So I have "the." So if I guess the next character in the key is a space, it's K. I give it character 3 is a space. Okay, and now this is turned in NEVE. So the next thing here is almost certainly R. So that's number 1, location 4 is an R. And 1, location 5 is a space. And this is Yule, so this is probably a space. So that's 2, location 6. All right, and that sort of thing. It's you can see how they did it with just pen and paper, with no computer at all. But you can pretty quickly do it this way. And if it helps you, I can show you the script I wrote that did that. A little bit too big to fit on the screen. All right. But anyway, it does require a little bit of Python coding, or some language. You could, of course, do it in any language, but it is very simple. And so it's kind of fun. And you go down here, there's longer and longer ones. And this one takes a while, but it's really not that hard if you write a good, efficient, interactive script. So anyway, you might like that.